Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, we'll continue talking about two-factor ANOVA, and we will look at the definitions of error and the score decomposition in two-factor ANOVA, how we partition the sources of variability. So to start, we start with this general definition of error. By now, we are pretty familiar with this definition of error. So error is the part of each score that's not accounted for by the model, right? This is how we define error in the data equals model plus error framework, kind of from the very beginning of the class. And another way to conceptualize this is that it's the difference between the score and the model, right? The data and the model, which means that it's the difference between the actual score and some model predicted score. So let's take a look at this leftover error variability and how we would conceptualize this. So looking at this plot, this is the plot that we just worked with in the last lecture, the last video lecture, where we had these lines that indicate the different group effects from this ANOVA. And what we're showing here is that we've added these distributions around each of these points representing a different marginal mean, a different cell mean. And there's a distribution of each point. There's a distribution of scores around that point. And the distribution of those scores, or the distance between scores and those cell means, is going to be our leftover error variability. Okay, so you can think about those points as essentially being the group effects or the model part of our framework. And what's left over, what's not predicting, what's not a part of the predictive model is the error. So looking at the score decomposition, again, now we have two different effects because we have two different predictors, two different factors, right? And so the score decomposition now is going to be that any score is equal to the grand mean plus the between group effect, what we call the between group effect of the first predictor, which is indicated by a J, and J dot indicates that this is going to be the group marginal mean, the difference between the group marginal mean and the grand mean, plus the difference between the group K marginal mean, this would be for the second predictor, and the grand mean. Okay, so we consider these the between group effects of each predictor. So we have the main effects of each predictor represented in our model. And then we have that leftover error. So this is how we get our data equals model plus error score decomposition. And so this is a slide you've seen before, I think during the first lecture for two-factor ANOVA, but we express each score as a systematic component that is essentially saying a group effect and a leftover error part. And the total variation across all participants, or think about that as kind of the total sum of squares, the total variation, the pie chart, is divided into three components. We talked about this already, but the three components are the systematic variation from predictor 1, the systematic variation from predictor 2, and then what's left, essentially. And we're going to use the sum of squares and the variances to quantify these different sources of variability. So these are the calculations for the between group sums of squares, also known as the predictor sums of squares. So essentially what this is saying is that for each predictor, we are going to calculate a sum of squares by using the number of scores in that cell multiplied by the between group effect of the first group squared plus the between group effect of the second group squared, and so on for all groups, essentially, for all groups that there might be. So we're saying that there would be J groups for the first predictor, or think about that as levels, okay? Let's say that that first predictor is gender, okay? That would be J is equal to 2. And then K is referring to the number of groups for the second predictor, the second factor. So if the second factor were video games, then our K would be equal to 3. So this is showing that calculation for the gender sum of squares. So we know that, again, each cell has 5 people in it. And so for gender, that means that each gender, they're equally balanced, that there are 15 participants of each gender. And so we take that number, 15, and then we multiply it by that group effect squared. All right, and we do that for each of the groups, and that gives us the sums of squares for gender, which is equal to 13.33. Then we do the same thing for video game, but now remember we've got 3 groups for video game, 3 conditions for video game, or levels. And so when we have 30 participants and they're equally balanced over these, that means that there's 10 participants per condition. And so that n is now going to be 10 for each of the multipliers of the between group effects. So we see that we have 10 multiplied by the group effect for the control group, 10 plus 10 multiplied by the group effect for the non-violent video game group, plus 10 multiplied by the group effect for the violent video game group. And each of those each of those group effects are squared. And that gives us the sums of squares for video game, which we see here is 65. And then for the error sums of squares, we compute the error sums of squares kind of as we do, as we always do. So for each group, we take that error value and square and sum it within the group, and then we sum those for each of the groups. Oh, and by groups here, I actually mean cells. So there would be 6 for each of the cells. Okay, and so this shows us how that those sources of variability break out in our particular example. So the total sum of squares in our example is 166, and then we just calculated the sum of squares for gender, which was 13.3, and the sum of squares for the condition, which was 65. And then we have the sort of leftover error sum of squares, which would be 87.7. And that gives us the total sum of squares of 166. So think about that total as being as the whole pie that's kind of broken out here into the different predictors and the error sum of squares. So to interpret these sums of squares, each of these sums of squares values represents the sum total variation that's due to group mean differences for each of these predictors. Then the error sum of squares is the sum total leftover variation in aggression that's not due to either of the group differences for either predictor, right? So the error sum of squares is how we always think about the error sum of squares. We've now just calculated an individual sum of squares for each of the predictors. And here's where we would find those values in the SPSS output. So this is from the test of between subjects effects table. You all are really familiar with this by now. So you know that in the second column is where we find these sums of squares. And I've highlighted here that there are now kind of three different calculations, 3 different calculated sum of squares that create, that are summed to create the total sum of squares. And so there's a video game predictor sum of squares and a gender predictor sum of squares. So the sums of squares are still used to calculate an overall R squared effect size. But the difference now here is that we are going to have an R squared effect size for the full model, and then we're actually going to have other R square that we can calculate for individual predictors. So the R squared effect size for the full model is, as always, as it was in regression, as you've always heard it up until now, it's the proportion of the total variation in the outcome that's due to the set of predictors, that's due to all of the predictors. So how we get this is that we sum the sums of squares from each predictor, okay? So the model sum of squares is the sum of the two predictor, the sums of squares for both predictors. And so you can see that calculation over here on the right side of the screen. So it's the sum of the sum of squares for gender and the sum of squares for video game condition divided by that total sum of squares, like we're used to seeing. And that gives us 0.472. So how we would interpret this is we would say that gender and video game condition account for 47.2% of the total variation in aggression. So it's really the exact same interpretation as the interpretation that we would use from multiple regression, where we have multiple predictors predicting an outcome. And here is where we would find that information in the SPSS output to calculate that R-squared. And as always, you know at the bottom of the tests of between subjects effects table here that the R-squared is actually printed out for us, and we can see that it's that calculation, it's 0.472. And the same guidelines for the full model R-squared effect size from regression apply here. It's the same calculation, it's the same R-squared. So we're going to use these same cutoffs. So a negligible effect is less than 2%, small is 2% to 13%, moderate 13% to 26%, and large would be anything greater than 26%. And these are our cutoffs for the full model R-squared, same as in the regression framework. This concludes the third lecture on two-factor ANOVA, and in the next lecture, we'll kind of carry on this discussion of R-squared, but we'll be looking at the individual component R-squared values, and then we'll also be talking about the full model testing.